You are given two beakers, A that can contain 5 milliliters of water and B 7 milliliters of water. There are no scale marks on the beakers, so the only volumes you can measure directly are 5 and 7 milliliters by completely filling the beakers. The question is, with just these two beakers, can you measure precisely 1 milliliter of water? You might have seen such a question as a so-called IQ test before, but in fact, actually everyone can solve it by just following their intuition. So let's follow our intuition and have a go. But before that, to make life easier, let's make a rule. Whenever we draw this, we mean 1 milliliter of water. Let's track the total amount of water in the two beakers. Where do we start? Initially, both beakers are empty, so let's write 0 plus 0 is 0. Let's start by filling in B first, so we get 7 milliliters in B and 0 milliliters in A. 0 plus 7 is 7. And let's say we transfer 5 milliliters of water to fill up A, leaving 2 in B. 5 plus 2 is 7. Now, obviously transferring the water from A back to B does no good, as it's reversing what we had just done. Emptying B does no good either, therefore let's empty A. 0 plus 2 is 2. After emptying A, let's transfer the 2 milliliters of water to A. 2 plus 0 is 0. And to repeat the process, we fill up B again. 2 plus 7 is 9. Again, not filling in A or emptying either A or B does not seem to do any good, so let's fill A with the water in B. Noticing there are 3 milliliters space left in A, so we get 5 plus 4 is 9. And empty A, 0 plus 4 is 4. Transfer 4 milliliters from B to A, 4 plus 0 is 4. Fill up B, 4 plus 7 is 11. Transfer 1 milliliter from B to A, 5 plus 6 is 11. Empty A, 0 plus 6 is 6. Transfer 5 milliliters of water from B to A, 5 plus 1 is 6. And finally, empty A, we're left with 1 milliliter of water in B, which is exactly what we had wanted. Gladly, we bumped our way to a conclusion. But how do we interpret what we had done, and how exactly does this 1 milliliter of water come? Let's look at the problem again. And this time, let's focus on the total amount of water in the two beakers after each action we take. We saw in our solution that we only take the following three actions. 1. Fill up B from empty. 2. Transfer as much water as possible from B to A. And 3. If A is full, we empty all water in A. That being said, the total volume of water in the two beakers, after each action we take, must either increase by 7 if we fill up B, or remains unchanged if we transfer water from B to A, or decrease by 5 if we empty A. And if we look at our track sheet, we indeed filled up B, transferred water, emptied A, transferred water, filled up B, transferred water, empty A, transferred water, filled up B, transferred water, empty A, transferred water, and finally emptied A. Overall, we filled up B thrice and emptied A for 4 times. And as a result, the net water we had gained is 3 times 7 minus 4 times 5 equal to 1 milliliter. As can be easily generalized, to measure 1 milliliter of water with beakers of size A and B milliliters, we need to find two non-negative integers x and y, those like 0, 1, 2, 3, and etc., that satisfy the equation x times A minus y times B is equal to 1. We need to add A milliliters of water for x times to the system and remove B milliliters of water for y times from the system to obtain a final total amount of 1 milliliter of water. Because all the numbers here of interest, be it A or B or X or Y related to this equation, are integers, this equation has been given a cool name, linear Diophantine equation. For example, given two beakers, A of size 3 and B of size 5, we have the linear Diophantine equation, x times 3 minus y times 5 is equal to 1. Noting 2 times 3 minus 5 is equal to 1, this linear Diophantine equation has a solution. In specific, it tells us filling in A twice and emptying B once will give us 1 milliliter. Also, noting 2 times 5 minus 3 times 3 is also equal to 1, we know filling in B twice and emptying A thrice should give 1 milliliter as well. So this linear Diophantine equation has more than one solution. We had explored how solutions to linear Diophantine equation can solve our measuring problem. But do measuring problems like this always have a solution? In fact, no. It's not always the case that we can find such integers to satisfy the Diophantine equation. For example, if you're given two beakers of size 6 and 3, you cannot measure 1 milliliter of water no matter how hard you try. With a equals to 6 and b equals 3 in the Diophantine equation, we have x times 6 minus y times 3 is equal to 1. But there are no integers x and y that satisfy this equation, since the left-hand side of the equation is always a multiple of 3, but the right-hand side, 1, is not. Indeed, whichever step you take, the volume of water in the two beakers, in total, is a multiple of 3, impossible to be 1 milliliter. So what combinations of beakers allow us to measure 1 milliliter and when not? To address this question, let me introduce two concepts: greatest common divisor, abbreviated as GCD, and coprime, and also a lemma called Bezout's lemma. For positive integers a and b, the greatest common divisor is the largest positive integer c that a and b are both a multiple of. We denote the greatest common divisor of a and b as GCD of a and b bracket. If GCD of AB is equal to 1, we say a and b are coprime, otherwise we say they're not coprime. For example, 5 is a multiple of 1 and 5, but not a multiple of 2, 3, or 4, and 7 is a multiple of 1 and 7, but not a multiple of 2, 3, 4, 5, or 6. The largest positive integer that 5 and 7 are both a multiple of is 1, so the greatest common divisor of 5 and 7 is 1. 5 and 7 are thus coprime. Another example, 6 is a multiple of 1, 2, 3, and 6, but not a multiple of 4 or 5. And 3 is a multiple of 1 and 3, but not a multiple of 2. The largest positive integer that 6 and 3 are both a multiple of is 3. The greatest common divisor of 6 and 3 is 3. 6 and 3 are thus not coprime. Bezout's lemma then suggests that if two given integers a and b are coprime, that is, their greatest common divisor is equal to 1, then there exists integers x and y that satisfy the linear Diophantine equation x times a minus y times b is equal to 1. So the measuring problem is solvable. Why is that the case? Basically, it's because x times a minus y times b can only be a multiple of the greatest common divisor of a and b. Therefore, if GCD, the greatest common divisor of a and b, is greater than 1, then x times a minus y times b must be a multiple of some integer greater than 1, thus cannot be 1. In other words, the measuring problem has a solution only if the greatest common divisor of a and b is equal to 1. Let's view this statement via some examples. With two beakers of size 12 and 9, because the greatest common divisor of 12 and 9 is 3, one can only measure volume of water that is a multiple of 3, and it's impossible to measure 1 milliliter of water. With two beakers of size 12 and 7, because the greatest common divisor of 12 and 7 is 1, by Bezout's lemma, it's possible to measure 1 milliliter of water. In specific, by noting 3 times 12 minus 5 times 7 is equal to 1, we need to fill in the 12 milliliter beaker thrice, empty the 7 milliliter beaker 5 times to obtain 1 milliliter. And by the way, this is Bezout, an 18th century French mathematician. There are other quite interesting applications of the greatest common divisor. Ever since thousands of years ago, the Chinese had adopted a special chronology called sexagenary cycle. Different from how years are numbered now, 2021, 2022, and so on, sexagenary cycle gives each year a special name by joining two Chinese characters from the two lists. The first list composes of 10 characters representing first, second, third, etc. The second list composes of 12 characters, more commonly known as their corresponding 12 zodiac animals: rat, ox, tiger, rabbit, dragon, snake, horse, goat, monkey, rooster, dog, and pig. We can make a 10 by 12 table with these characters. Last year, 2021, is 辛丑 year, and this year, 2022, is 壬寅 year. Each year, the next character from each list is drawn, so we always move to the downright diagonal grid. When we finish a list and reach the boundary of the table, we go around and start from the beginning of that list again. There seems to be a combination of 120 years with this table, but in fact there are only 60 years in a cycle, as suggested by the name sexagenary cycle. By coloring the years that follow, we see only half of the grids are filled. Why is this happening? Let's label the years by summing the orders of the components of its name. For example, year 2021, 辛丑, composes of 辛 with order 8 and 丑 of order 2, so 8 plus 2 is 10. Year 2022, 壬寅, composes of 壬with order 9 and yin of order 3, so 9 plus 3 is 12, and so on. We notice for every year, its label is an even number. Even if we had wrapped around the boundaries of that table, it's still an even number. However, only half of the table are even grids, and the rest are odd grids, hence only half the grids can be occupied. It's quite similar to what's happening in the measuring problem. The greatest common divisor of 10 and 12 is 2, so that only the even grids, those that are multiples of 2, can be reached, not the odd ones. Therefore, only half the grids are covered, and there are 12 times 10 divided by 2 equals to 60 years in a cycle. This 60, in fact, also has a name. It is called the least common multiple of 12 and 10, which we denote by LCM, bracket 12 and 10. If we adopt another chronology, say combining 9 English characters with 6 Greek letters, because the greatest common divisor of 9 and 6 is 3, only 1/3 of our chronology table will be covered, wherever we start. As a result, we will get a cycle of 9 times 6 over 3 is equal to 18 years. If we had 10 English characters with 7 Greek letters, because the greatest common divisor of 10 and 7 is 1, 1/1, all of our chronology table will be covered. Wherever we start, we can wrap around the entire table. So this chronology gives us a cycle of 7 times 10 over 1 is equal to 70 years. In fact, there is a related theorem called Chinese remainder theorem that addresses such phenomena. Chinese remainder theorem states that for integers a and b, if greatest common divisor of a and b is 1, then the product group CA and CB is isomorphic to CA times b. In terms of our calendar, it's basically saying that the A by B chronology table we created can be unwrapped to form one strip of continued years with length A times B, only if the greatest common divisor of A and B are 1. Well, I guess I had tried to cover too much without sufficient details, but obviously one thing you could take away from this video is, let's recap, that given any two beakers of integer volumes, even very large ones, say 48 milliliters and 137 milliliters, by noting 137 is a prime number and thus is co-prime with 48, you can tell that they can be used to measure 1 milliliter, for sure in some way, without forming the hundreds of steps procedure by hand. Sounds like a cool trick, right? Plus, even if you find using common divisor and stuff to unwrap a calendar not quite persuasive, nor too attractive perhaps, concepts such as the greatest common divisor, the least common multiples, and etc. still do have lots more interesting applications for you to explore.